We have one last piece, one last conceptual piece to add to Maxwell's equations before we're done writing them all down correctly. We've already established this week that induction happens. In other words, Faraday's law tells us that if you have some time-changing magnetic field, that generates an electric field, and that is given by this equation. So time-changing magnetic fields generate circling electric fields. But it turns out there's a symmetry. So it also turns out that time-changing electric fields will generate a magnetic field. Okay, and so we want to learn about that. The best evidence for this is light waves. Light waves don't exist unless you have this trade-off between magnetic fields. So light waves are a packet of electric and magnetic fields that travel together, and it works by oscillating magnetic fields, generating electric fields, generating magnetic fields, and it keeps going that way. We'll talk about light waves in a couple chapters here. But the most often used justification for this is looking at the charging of a capacitor. That's what's in the book. If there's a problem with charging a capacitor and the current set of Maxwell's equations that we have, there's a missing term. And so let's show how that works. So let's imagine charging a capacitor. We're going to have a very special capacitor arrangement that has some symmetry to it. So instead of having a capacitor like this with wires and a battery charging it, let's imagine a big, a fat wire like this that's infinitely long. So this goes on to infinity, and then I have a cut in it. Okay, so I have a cut in the wire. Didn't draw that very well. Okay, so let's imagine I have a cut in the wire that's a certain, gap distance, but otherwise it's an infinite wire. And I imagine I'm charging this capacitor, by forcing some current I here. That means that some current I has to be forced away this way. You can imagine these legs are far away connected to a battery, and the way this current gets pushed is that, like up here, I'm going to have current coming out of the battery here, and the battery will pull current back here. Okay? Now, the only way this can happen with a cut in the circuit is that you get charges, right? So this is going to charge up positive, this is going to charge up negative, and it will continue to do that until the push from the battery matches the voltage difference across these two faces. Okay, so as soon as this capacitor here, this break in the line, has enough voltage drop across it to equal the EMF of the battery far away, the current will stop flowing. But until then, you'll charge up the capacitor. Okay. All right, so let's see. Let's analyze this situation. So here's what I want to think about. Let's think about that same wire. Okay. Had a better drawing on the previous page, but anyway. And let's imagine that this current is going to be transient. Okay. But let's imagine looking at this current at an instant in time. And let's use Amperes Law. So Amperes Law, if you remember, there's two forms I can write. I can write curl B equals mu naught J, or the equivalent is that the integral of B dot dl is mu naught I enclosed. Okay, right. And just to remind you that I enclosed is going to be defined as the current that crosses some area. So we'll have a J dot dA, and the area here is bounded by this loop. That's the idea. Okay. All right. Now I didn't give myself much room here, but if I look, what I can do is look at this wire and pick a loop that looks like this. Okay. And then there's many surfaces I can choose here. Okay. Now there is a symmetry here. The symmetry tells me that if I'm far enough away from this gap, so I can move this loop very far away, so the gap is not very close to this. And the way I've drawn it, that's not at all clear. But if I move very far away from the gap, I have a pretty good argument that the field should be invariant in this direction, in the z direction. Okay, it only becomes potentially varying in space when I come close to this gap. But if I'm far away, I don't see that. And I also can argue that the magnetic field should only depend on um, the radial direction. Okay, so in other words, the magnetic field should loop around this current. So as I've drawn it, it's going to do, circle like this, right? And you imagine I have enough symmetry to argue that the integral of b dot dl, okay, on that loop, switch back to black here, should be something like b theta times 2 pi r, where r is the r of the loop, okay? And then on the right-hand side, I'm going to have the current enclosed. Now the trick here comes with something that I've been saying all along. So when I pick a bounding line, so I've picked my bounding line. So this is my loop. My Amperian loop is here, right? There are infinitely many surfaces that will fit that loop. So one of them is the surface here. So with that surface, there's a clear current enclosed. And that current enclosed is just mu naught times, current enclosed is just I. So this is going to equal mu naught times I. Okay, for the flat surface. Okay, but however, if I take a surface where I blow it up like imagine this is a soap film and I blow it up, okay, I can draw a surface that stretches like this, goes between here and then comes back, and the surface kind of extends like a bubble like that. Now, strictly speaking, if I look at this equation, the current enclosed is 0 because there is no current. There's no surface current, no current density passing through that surface. Okay, so in this case, I would have 0. Okay, so let me do it this way. Mu naught I enclosed is that. Here it's 0 for my bubble surface. Mathematically, those should be identical. Okay, what I meant to say is you are allowed to choose either surface. Okay, there are infinitely many surfaces. I can blow that bubble up as big as I like, and mathematically it satisfies this expression. Okay, that has to do with Stokes' theorem. Okay, so I have a problem here. So I have a situation where in one case I would find the magnetic field should have finite value on that loop, and if I choose another surface, I find it has to be 0. Okay. Now, this, it turns out, is wrong. Okay, we're missing something here. It turns out that these have to give you the same answer. So it has to be the case that this equals mu naught I when I'm all done. But the question is how? Because again, if I look at this surface, there is no current that passes through this surface. In this gap here, there is no current. Okay, so I would say that I enclosed is 0. Okay. So the way that we rectify that is by acknowledging that there's a different term, okay, that was discovered by, oh goodness, I should know. There has to be additional term in the equation so that the right-hand side doesn't go to 0, but in fact equals this, okay, to make it consistent. So there's an additional term. This was discovered by Maxwell as he put together his set of equations. And the term looks like the following. So you modify Amperes Law. So Amperes Law, let's write the integral form. Integral of b dot dl. I have the term that we know already, mu naught integral j dot dA, or the mu naught I enclosed, but there's an additional term. And the additional term looks like the following. Mu naught epsilon naught, okay, times ddt of integral of e dot dA. Okay, so this looks a lot like the term that we got for Faraday's law, right? So this term, what it tells you physically is, again, that time-changing electric fields generate magnetic fields, okay? Now, if I write the differential form of this equation, it looks like the following. Curl of B. So magnetic fields will circle around currents and will circle around time-changing electric fields, okay? So now this is the correct form of Ampere's law, and we now know all of the physics in electromagnetism. You have all the terms and all the physical effects are there. Okay. All right, now if I include this effect, here's how it fixes the problem. So let me show you that. So if I look now at the the situation I showed before. Okay, so here is my wire. Imagine I have a current I that flows in. The rate of change of charge on this plate has to be equal to I. dq dt has to equal I. Okay? Now what I'm going to do is approximate these as parallel plates. Okay. Now it turns out even without approximating it, I'll find that this problem is solved. Okay. But approximating it gets me to the answer quickly. So if I approximate these two as parallel plates, I know that the electric field, and let me just make some room here. So looking at these two plates, I have some charge that's showing up on this one. I have minus charge that's showing up on this one. The electric field in the middle here, E, will be sigma over epsilon naught, okay, which of course is just Q over A epsilon naught. Okay, sorry, let me go to the next page here. And so if I look at d E dt, what I find is that it's equal to I, so dq dt, over epsilon naught A. Okay? All right, and again, I have Q over epsilon naught A. I take the time derivative, I get an I on the top because of that. Okay? And so now, if I look at my Ampere's law in this case, and let's pick a very particular surface. So I'm going to pick two surfaces. I'm going to pick my loop to, well, it actually doesn't matter, but to make life easier, let me pick a loop that is flat with a flat surface, and then the alternative will be a cylindrical surface that cuts through the middle of the cut. Okay, so that this surface is flat, just like this surface, okay, over here, and here's my cut. All right, so if I look at this additional term that I added, so now if I look here, I have no electric field, no dE dt, but I have mu naught I enclosed on the right-hand side. Here, I have no j dot dA is 0. There's no I enclosed, but I have this new term that I just wrote down, mu naught epsilon naught d dt of the integral of E dot dA. Okay, and so in this region, E is constant. I made the argument that I have parallel plate capacitor kind of set up. E is constant, and so this is the same as mu naught epsilon naught A times dE dt. Okay, and as I just wrote down, this is the same as mu naught I. Okay, so I go back up and look at dE dt, plug it in, and all is well. Now I have the same right-hand side no matter what surface I choose. Okay, so this is required to make this equation consistent, but it's also required to explain light waves. Okay, so this term, which is called the displacement current, so this this term here is called the displacement current, is required to explain this phenomena of, this is really a mathematical argument, it seems like, right? I'm just changing the surface. But it's also required to explain light waves. So if you look at this scenario with the charging wire, what this tells you is that the source of magnetic field is constant throughout this whole region. And so in fact, the magnetic field does not vary in space as you go across the gap. So in fact, my original argument, and I didn't have to argue that the wire, this loop that I drew here, was far away from the gap, because in fact the symmetry is preserved, because the right hand side of this equation is uniform along the whole wire, it turns out. Okay, all right, let me stop